Welcome. Today we're going to present a compute resiliency update. We have three presenters. I am Lidia from Nvidia, Arzhan from Intel, and Adam Cron from Synopsys. Our presentation includes three topics. First, a quick update on the specification. Then information about how we're cooperating with the academic community and plans for future work. And then Adam is going to present SDC embedded for a low-level testing. First, our SDC definition. So we're considering that silent data corruption causing computing system is a faulty machine that is characterized as SDC causing if we identify a bug-free workload, any kind of test or workload or screening tool that produces incorrect results without any indication from the hardware that an error was detected. Today we are at the revision 1.0 of the specification, which was released a few weeks ago. On this page, you see at a high level what the specification contains today, as well as all the contributing companies and the contributing engineers who have developed this specification. Our initial mission was to standardize an information exchange format for communicating about data errors and to enable collaboration across academia, silicon vendors. And we had three phases. First was, crawl, which is just provide information about how different chipsets failed and establish a process to track contributions of different pieces of silicon and provide access to the data. Then in our walk phase, we wanted to have test development frameworks that are open source that can be used to develop new tests that could detect silent data errors, either in a lab environment or in a data center environment. And our run phase was to establish processes and methods to evaluate different solutions for detecting silent data errors and suspect systems, and create new techniques by researching these silent data errors in different systems and installations. Currently, I think we are in a transition from walk to run. We have completed the exchange format definition. It is in the 1.0 spec. Also, we have established several test development frameworks. Arzhan is going to cover different test development frameworks from the participating companies. We have defined metrics for evaluating the test efficiency. Future work is going to define additional metrics that are going to look at software resiliency, hardware resiliency. And then we have funded 6 academic teams that are going to advance the state of the art in the detection and understanding of silent data errors. Our metric, as mentioned, is the test efficiency. It's a fairly simple metric. It's the inverse of time to fail. It has additive capabilities because, as we know, in a data center, we have different types of hardware, different types of SKUs. We may even have different types of software developments depending on the function that a different cluster has. So applying a one-size-fits-all for a metric like this may not be realistic. So then the hardware can be divided in subpools and the efficiency can be calculated for every subpool. Also, depending on the type of fault that we are looking at, we can apply a weight factor where, if we're very concerned about a new error that we detected or an existing error, we can weigh it higher than 1. Otherwise, we can weigh it less. And it gives flexibility to the user of the metric to understand what is going on based on their interest. One may wonder, okay, well, what happens if we don't detect any errors? Well, then time to failure is infinite, test efficiency is 0. In the case where an error, a silent data error, causes a timeout, then the duration of the timeout represents the time to failure. And I'm going to invite Arzhan to talk about test frameworks.
Hello, I'm Arzhan with Intel. So we're going to talk a little bit about open source frameworks, and there are 3 of them as part of this work stream. The data center GPU management by Nvidia is actually a monitoring tool. It's an agent that allows you not only to test your GPUs, but also monitor them. It's a well-known tool from Nvidia. It allows you also to develop your own tests and plug them in, so you could run them and, with the objective to detect the silent data corruption. AMD Open Field Health Check is an orchestrator. It's also open source, obviously. It allows you to aggregate multiple binaries, multiple executables, run them, and report the results in a uniform manner. At Intel, we have OpenDC-Diag. This is something that I work on, and we'll be happy to talk about it. We had quite a success with it. It's a result of open sourcing part of the product that we have internally at Intel, and it's a very robust framework that has solid API. We have also the documentation for writing new content, new tests, and it's exclusively focused on detecting silent data corruption. Please go ahead and check out all these frameworks, and if you're interested, I'm specifically an expert in OpenDC-Diag, you can talk to me. About future work, we at industry is currently, it's a little bit of whack-a-mole games, because with process and with changes in process, changes in design, and you cannot expect that the next generation CPU or GPU will be subject to the same type of errors. In other words, that one test that was successful on one generation will not necessarily, and almost always not, is as successful on the next generation because the IP changes. So we are obviously focused on that and focus on our current generations, but the problem requires a long-term solution for which we really do not have time to sit down, step back and look at the bigger picture, so to speak. And this is why we are partnering to sponsor the research in academia towards creating a solution that would be more sustainable, that it would allow us to predict and identify early potential issues with SDC in the chip designs, and multiple companies are collaborating as part of this work stream on that. 6 universities has been evaluated. The scope of the future work as part of this work stream is we'll be focused a little bit on AI and machine learning accelerators for the next revision of the specification. So the workstream funded these 6 universities to conduct research in the areas SDCs, and the key to the learn-term solution here is modeling, proper modeling, taking into account changes in the process, in the manufacturing process, and in chip designs. Because really SDC, yeah, there's a big difference between bug and SDC. Bug is something that you designed into. SDC is just, collection of, events that led that part of the chip is just malfunctioning. And even worse, malfunctioning in a silent manner that is really hard to detect. There's also been another round of grants for the university, so this list will be extended, and the scope of the research will be expanded as well. This call to action is, yeah. So please join the workstream. Help us change this really challenging problem, which is silent data corruption. Review the latest specification and provide feedback, and submit any feedback that you might have to the workstream using the email provided here. With this, this is it. I'll pass to Adam. Thank you so much.
Thanks very much, Arzhan. So I'm Adam Cron from Synopsys, and in case you're curious, Synopsys sells software and IP for getting your idea all the way down to a fab so you can design it or build it at the likes of TSMC or Samsung or GlobalFoundries or Intel, et cetera. So I'll be talking about how to improve our ability to detect issues or diagnose them in the system, because I think we can do a little better than what you're being given so far. So let me start with silent data corruption and why it happens. Number one issue is process marginalities, which is pretty much out of your control unless you are a fab. But the next one, test coverage and test escapes, that seems like the number one issue that we can address to solve this silent data corruption issue. And if you look at the quote on the right-hand side of the slide, you can see that the silent data corruption issue happens because of temperature, voltage, frequency, data set, instruction sequence, exacerbated by some operating conditions, design errors, et cetera, et cetera. Anyway, pretty complicated corner case. And you might be wondering, well, gee, if you tested it and you shipped it to me, why is it still broken? Well, let me keep going. Here's the number one issue of test escapes. We test the chip in the factory using some test patterns. And the test patterns, in this case, we're going to try and test this circuit. We'll apply some pattern from these flip-flops here. We'll scan that pattern in, and we'll test that XOR, and we'll test this XOR this way, and et cetera. We'll test that XOR. Very easy testing the XORs. And then look at that. We got 100% coverage, but we never tested this long path. And if you remember the previous slide, temperature, voltage, blah, 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 that's kind of a corner case, which if you encountered it in the system, a small, tiny defect might actually not work and cause that path to fail. So the test patterns then get applied at the factory, and I'm going to eventually get out to the field. But customers are currently using their high-speed interfaces to get the test data into the chip at all. So using USB or PCIe and taking that very high-speed and high bandwidth interface on the side of the chip or side of the package and shoving that data in as fast as possible. And then we have like a factor of anywhere between 800 and a couple thousand X to slow that data down and get it to the cores that we're trying to test at, let's say, 50 to 200 megahertz shifting inside the core. So we have lots of bandwidth, we're getting lots of data in, but keep in mind that this pathway goes through the controller, through a piece of specialized DFT hardware, to ratchet it down, and then through a special test fabric. And that test fabric is basically a side channel or an out-of-band pathway from at least those green boxes to all the cores and other little things you're trying to test inside the design. So while you're doing test, you're really not messing with the other fabric. So if you can envision using that fabric in the system to do testing in the field, you're actually not impeding the regular flow of data between these different cores. You're using this out-of-band fabric. So what sits on that fabric? Here's some examples. Test compression. So everyone uses compression now to compress their patterns. This enables you to apply any kind of test pattern to test the core. Scan chains are used to move the data finally from that fabric down into the core. And this gets very good coverage, as we've seen, 100%. But still some faults fall out. But it's a nice avenue to put a very specific pattern into the design. And if you look at these little red circles here as I go to the next slide, we can reuse that infrastructure to do built-in self-test. So built-in self-test can use little or no data to test a core, depending on what level of coverage you need. And you can easily do it in an embedded situation out in the field. For memories are very well covered with memory-based operations and even repair operations to basically recapture the yield of failed memories as they're manufactured, and also can be fixed out in the field as well by reclaiming parts that become slowly defective once it's realized that these things are defective. There's also tons of sensors inside your design. And again, these are all accessible on this out-of-band fabric, which we're using for test, but also could be using in the field. Voltage sensors, temperature sensors, process marginality, process sensors, et cetera, ring oscillators, those things are available. And we can look at those almost any time without impeding the normal operation of the design. And then finally, I would call these kind of functional monitors, error detection and correction for memories, CRC checks for big data chunks, triple module redundancy, for example, on a particular register that you wanted to have checked and make sure it always works. You can make 3 of them and they vote so that 1 bit flip on triple module redundancy could still work. Built-in self-test, dual-core lockstep is kind of an expensive idea for detecting an error, but it will detect an error. So lots of things out there available in your chips already if you could only use them. So keep that in mind. So how are we doing on a kind of a template of a design? So for memories, I think we're doing very well. Error detection and correction is catching a lot of issues. Repair is available. So I think we're fairly well covered for memories. The networks are one-to-one wires, have parity, and other kinds of checks can be done on the data. Again, issues certainly arise, but they're detectable, not necessarily silent. For registers, you can put in triple module redundancy. For finite state machines, you can actually synthesize fail-safe state machines so that a single bit flip will actually still end you up in the same state, but throw an error, which then you can flag to the system to say that something went wrong. However, things like your floating point unit or your arithmetic unit, which are giving you the wrong answers and you cannot hear them, that's the silent data corruption issue. Logic BIST could be periodically run here. Dual core lockstep, again, a little more expensive. But there's also ways to use the DFT infrastructure and sensors to try and detect aging issues which might occur and might also be used to find these kind of very sensitive or marginal issues. So we've got this great pathway between the top of the chip through, let's say, PCIe into the scan fabric to do all our tests. Wouldn't it be cool to attach a RAS engine, as we've been discussing, to this DFT IP in the controller, so that when we can take all of our sensors and actually observe them along this out-of-band fabric, or maybe even in-band, possibly, for some of these sensors, and do testing at a very deep, deep level to try and detect these issues. And then this RAS engine could do a little compute, figure out if things are working okay, is it working the same way that it worked yesterday, et cetera, or pass that data up to the cloud, do some big data crunch. Does this core work better or the same as that other core? Is the nuclear reactor causing bit flips over here but not over here? Things like that. So the call to action here is to tell your chip providers to give you lower level access to the DFT and infrastructure that's already available in your chips. And we should try and standardize that interaction with the DFT so that different vendors can plug and play and make use of the resources that are already in your chips, if only you had access to them. For more information, you can click on, about the DFT, you can click on atpg.com. Any questions for any of us?
Time for question. Can you come to the mic?
Yeah, thought-provoking ideas. In the automotive market, you already have the notion of running the test, from time to on intervals. And you do have to pause the machine, though, because if you want to use the scan chains and you want to use everything, your flops can't be doing functional flipping and scan chain flipping at the same time. So it's not free, right? I think there's a cost. You got to pause, you got to do this, and you got to get back to business as usual. Yes,
so good point. It might not be free. Some of those sensors are free, like path margin monitors are free. There's other ECCs per unit time is free. Drew mentioned, though, that he had to debug for 9 months to find his issue. And I've been listening to a lot of these data center folks. They're running regular software loads at the operating system level and trying to find random defects by throwing random data and random instructions at their system, hoping to find something, right? Wouldn't it be good just to take it offline for 3 seconds, and just periodically test something at, let's say, low voltage, high frequency, whatever it is, to kind of sensitize a marginal part.
Sure. So the other practical issue that will come up is economics, because
is what?
Is economics. What happens is that design times will go up, the chip area will go up a little bit, so there'll be a cost associated with every chip, and then we'll have to talk about, how much of that cost is worth it, and it's money one way or the other, right? It's not as simple as saying I can do it, I should do it. There's an economics question to be answered.
I contend it's zero extra cost because you've already got that stuff in there from the manufacturing floor.
It's not zero extra cost because you've got to now make sure that at runtime you can pause your machine and you can do all this stuff. So, and then there could be extra area because just because you added it for test doesn't mean it's going to work at production time. So there's at least a design cycle time, NRE cost to the adder to develop the chip that has that capability, right? Capabilities don't come for free, right? And there could be chip area cost. And it may not be huge, okay? I think your point is that the vast majority of what you need might be there. It's not going to be zero, right? And so just highlighting, right? I'm not looking for an answer. I'm just saying that there's an economic side to the equation as well.
I think you mentioned automotive space, and in that space, the usage model is very different than the data center. A car starts multiple times a day. There is time at every start to perform self-tests. So I think the application there is probably very different than in the data center, where some of these tests would have to be done at runtime.
Right.
So yeah, the challenge is on a different scale.
Yeah, thanks for acknowledging that, yeah.
All right, we have time for one more question. Go ahead.
Yeah, silent error can occur randomly, right? Anytime. Yes?
I didn't understand what you said.
Silent error can occur randomly anytime. Yes?
Yes.
Yes.
Okay. And the testing we are doing is very deterministic. Yes?
Correct.
So how are we ensuring the testing we're doing will actually find the random silent error before it actually occurs?
How do we ensure that the test could find before something is deployed in production.
Before the silent error actually occurred, it was time t0, right? Machine booted. And let's say we run the test time t plus n. But between time t0 and t plus n, silent error can happen. So the impact of silent error will already occurred.
Yeah.
Any thoughts on that? I'm not saying that there's a problem here, but I'm just trying to understand what's your thought process, how you want to address that.
It's a good point. Silent data errors will happen. I don't think either through testing or through checking data integrity at runtime or through design of the silicon, we can always cover 100% all the possible corner cases to avoid errors. So because of that, I think that there will be incremental learning over time. We learn about the new usage models. The new usage models can be built to have additional redundancy in them, both software and hardware, depending on where the errors would have the most impact if they occur. So yeah, my opinion is that the industry will evolve and become more resilient to silent data errors.
I can also give a particular use case. So automotive has a fixed set of patterns that it runs all the time to a certain level of coverage. Data centers have years, but they don't have to hit any coverage, really. They just have to keep running. So we could make use of that embedded scan path access to continuously, for example, feed brand new patterns to eventually exhaustively test some core, all the cores, right?
But that doesn't help there. Randomness of the
You
silent
say that
error.
now.
No, randomness, silent error can happen anytime, right? And by the time you're running it, silent error already occurred before that, right?
Yeah, no, I'm not talking about the same pattern set. I'm talking about just like the software you run is random, the patterns you apply can be continuously changing and eventually trip that particular issue.
Yeah.
You're playing with probabilities for sure.
Exactly.
And,
I think we are out of time.
Okay.
Rest of the question can be taken offline. So let's thank our speakers. That also concludes our hardware management track. So thanks everyone who were here for the whole track and some of the sessions during that. Thank you.